Hello, this is lesson 3.6, rational functions. So again, at any point during this um, lesson, feel free to pause the video and try it on your own to do the examples. Okay, we're going to be talking about rational functions. So a rational function is a function whose rule is the quotient of two polynomials. So such as there's f of x equals 2 over 1 plus x, f of x equals 3x plus 2 over 2x plus 4, and then f of x equals x squared minus 2x minus 4 over x cubed minus 2x squared plus x. A rational function's rule can be written in the form of, so f of x equals p of x over q of x, and q of x does not equal 0. Um, so in this graph, we have f of x equals 2 over 1 plus x, and we can see that there's like two sections of it. So we have a horizontal asymptote and we have a vertical asymptote. The vertical is x equals -1 and the horizontal is the y-axis. And then so the graphs do not cross the asymptotes, and we'll talk more about it in a little bit. So the domain is restricted to all real numbers that do not cause the denominator to be 0. So we have to make sure that when we are looking at the domain, we need to exclude when the denominator is a 0. Okay, so let's start with this first example here. Y equals 1 over x. We have the graph of it right here. Let me actually just draw a line here so that now if we look at the denominator here, we already can see that x cannot equal 0 because then we would be dividing by 0, and that means that it would be undefined. So our domain is going to be from negative infinity to 0, and 0 is not included, and then from 0 to infinity. And or we can write it as a set x is such that x does not equal 0 and braces. Now, if we look at the graph, we can see that it does not cross the x-axis and it does not cross the y-axis. So x equals 0 is going to be our vertical asymptote, and then our horizontal is y equals 0. Um, this one I forgot to write. Should be or. So the U sign means or. Okay, let's look at our next example, which is y equals 1 over x squared. And again, we need to look at what number makes the denominator 0. So again, it's x cannot equal 0 because that would make the denominator 0 and the whole thing would be undefined. So our domain again would be from negative infinity to 0 or 0 to infinity. And 0 is not included, so everything's inside parentheses. And then we can write it as I said, x is such that x does not equal 0 and close the braces. Again, if we look at the asymptotes, we have the y-axis, the x-axis, y equals 0, and we have the x-axis. No, y-axis, x equals 0. I'm writing as I'm saying. So this is our horizontal, and this is our vertical. And you can see that the vertical comes from here. We'll talk more about the horizontal in a little bit. Next example, we have y equals x squared minus 1 over x. Again, the denominator cannot equal 0, so x cannot equal 0. So we already know that x equals 0 is going to be the vertical asymptote. And our domain is going to be negative infinity to 0 or 0 to infinity. And if we write it with the set notation, x is such that x cannot equal 0. We have another, so we don't have a horizontal asymptote for this one, but we have a slant asymptote, which that one is y equals x. Again, we'll look at how to, figure these out in a little bit. Next one is y equals x over x squared minus 1. So now x squared minus 1 cannot equal 0, or we're going to be dividing by a 0. We're going to add 1 to both sides. X squared cannot equal 1. Well, we're going to take a square root and add a plus and minus. So x cannot equal positive or negative 1. So we need to rule out both of those now from this. So our domain is going to be negative infinity to negative 1, or negative 1 to 1, or 1 to infinity. And if we write it in the set notation, it would be x is such that x does not equal negative 1 and 1. Okay, if we look at the graph here, we can see that there's our x equals 1, and there's our x equals negative 1. Our vertical asymptotes, and then we have our horizontal one that is y equals 0. Okay, so moving on, a rational function will have values at which the graph is undefined. So these values show up as either holes, holes. If the function is not in the lowest in its lowest terms, or as vertical asymptotes, VA. Okay, so let's look at the definition of a asymptote. That is a value the function approaches but never gets to. Distance gets infinitely smaller. So as you can see here, when we look at these graphs, the graph, it keeps going towards the asymptotes, but it never touches it. Okay, So now we're going to look at holes and the vertical asymptotes. They are determined by the domain, which is the denominator of the function, and can be more than one, as we saw. There are, in that last example, we had two. So make sure that you're aware of that. So again, holes occur for any values from the denominator that factors out because the function was not in lowest terms. Vertical asymptotes occur for any values from the denominator that remain. Each VA is like a brick wall. It is never crossed. And it's asking us to find the vertical asymptotes and holes of each example of the examples of rational functions above. Well, we did find the vertical asymptotes. None of these have holes because we're not able to factor anything out. They are factored to the lowest terms, and we'll look at an example where we are actually our next one is an example where we're going to be factoring them out. Okay, so practice. First, hold on a second. Before I do any of that, let me draw some lines here so that I'm not trying to keep all of it where it's supposed to be. Okay, so our first one is y equals x plus 1 over x squared minus 1. Now, we are able to factor this out. So our top is x plus 1, our bottom, x squared minus 1, can't be factored out to x plus 1, x minus 1. It's the difference of squares. And now we can cancel the x plus 1. So we end up with 1 over x minus 1. So this is at its lowest terms now. So what did we do? We factored. Second, we're going to find the domain, which x minus 1. And actually, so when we are finding the domain, we need to take this right here, like the original one, because that's what we've got. So x squared minus 1 cannot equal 0. Well, we already did this, and we ended with x cannot equal positive or negative 1. So the domain x is such that x cannot equal negative 1 or 1. Okay, now we're going to look at, do we have any holes? For the hole, we're going to look at what did we factor out. So we factored out x plus 1. Now we're going to see where does that equal 0. When we move the x, we get x equals negative 1. So this means that we have a hole at x equals negative 1. So what does that mean? If we look at our domain here, we already used that. We still have the 1. That means that our vertical asymptote is going to be x equals 1. Okay, let's try another example. Again, we need to factor this first. We can take out the greatest common factor on the numerator. So when we take out x, we've got x minus 3 left. Now, factoring out an x from the denominator as well, we get x squared plus x minus 2. And then I'm going to factor even farther the x squared plus x minus 2. So when we do that, we get, so our numerator can't be factored out anymore. Our denominator, it's going to be x, x minus 1, x plus 2. Okay, so the only thing we can factor out here is the x. So this was our step 1 where we are factoring. Our step 2 is going to be looking at the domain. So now our domain, again, means that whatever values we've got here in the denominator, none of those can equal 0. So x cannot equal 0, x cannot equal 1, and x cannot equal negative 2. Remember, we set these to equal 0 like we did here, and then we solve it. Okay, so our domain x is such that x cannot equal negative 2, 0, and 1. Now, that is our domain. Now we're going to go ahead and look at which one of these numbers, negative 2, 0, and 1, did we factor out, or did we, were we able to factor out? It's the x, so that means that x cannot equal 0 will is the whole. So we have a whole at x equals 0. Now, these other ones, x is 1 and x is negative 2, are going to be the vertical asymptotes. So x is negative 2 and x equals 1. Again, what we do is we exclude all of these, the denominator that is going to equal 0. Those are excluded from the domain. Then we go backwards and look at those x values and determine, did we factor anything out? And yes, we did here. And then the rest are going to be your vertical asymptotes. Okay, let's try this next one. So x squared plus x equal, or x squared plus x divided by x squared minus 4x minus 5. Okay, well, on the numerator, we can again factor or take x as the greatest common factor, and we end up with x times x plus 1. On the denominator, when we factor it, we end up x plus 1 and x minus 5. So x plus 1 and x plus 1 cancel out. This is our step 1. And we end up with x over x minus 5. But now, we need to make sure that we remember that x cannot equal negative 1, and x cannot equal 5 either. Those are the values that will set this original denominator to become a 0. Okay, so our domain here is going to be x is such that x does not equal negative 1 or 5. Then what did we cancel out here? It was the x plus 1, so x cannot equal negative 1. We have a whole at x equals negative 1. And the 5 is going to be the vertical asymptote. Okay, next one. The top one factors to x plus 4 and x minus 1. The bottom, we can take out the greatest common factor, and then it ends up being x squared minus 2x plus 1. Now, so we are doing the first step here. So numerator is x plus 4 times x minus 1. Denominator is x. And then we can factor the x squared minus 2x plus 1 to x minus 1 squared. Okay, so again, x cannot equal 0 and x cannot equal 1. We can cancel out one set of x minus 1s here. The domain is going to be x is such that x cannot equal 0 or 1. That's our number 2. Number 3. Now, here's the thing. In this case, there is no hole. Yes, I know we did cancel one set of x minus 1s, but we have another one here. So our vertical asymptotes that are left here are going to be x equals 0 and x equals 1. Okay, so again, there was no hole because we had one x minus 1 still left in the denominator. All right, let's go ahead now and review transformations. So use your knowledge of transformations and the examples on the previous page to sketch a graph of each rational function. So for this one right here, we have the parent function is this one right here. So looking at the graph, I'm going to go ahead and the parent function looks like this. Now, for the transformation, all we have is that negative in front, which means that we are reflecting across the x-axis. So it looks exactly the same, except that it goes down here, like that. We are still going to have the same asymptotes. So y-intercept, there's none. It does not cross the y-axis. Zeros or x-intercepts, none. It does not cross the x-axis either. Domain, well, what is excluded from this domain? X squared cannot equal 0, so x cannot equal 0. So the domain is x is such that x cannot equal 0. Our range, we start from negative infinity down here and go all the way up to 0. 0 is not included. Again, remember that that is our one of our asymptotes, like that. So vertical asymptote is x equals 0. Horizontal is y equals 0. Our end behavior, what this means is that when x approaches infinity, y approaches 0, which happens right here. So x is approaching infinity, y is approaching 0. If x, or when x is approaching negative infinity, So on this side right here, y is approaching 0. Okay, let's look at y equals 1 over x plus 2 minus 3. So this parent function is going to be the first one. So y equals 1 over x. So it's going to look like this and like this. So, our asymptotes are the y equals 0 and x equals 0. Okay, but what are we doing to this, what transformations? Well, this plus 2 takes it left 2. Negative 3 takes it down 3. So now we can look at the parent function here and figure out the asymptotes. I mean, we're going left 2, so our asymptote is going to have to be x equals negative 2, right? So that's our vertical asymptote. Now our horizontal asymptote down 3, so that's going to move somewhere here, y equals negative 3. So we can kind of sketch it where it's going to be. We know that our domain is going to be x is such that, again, that x plus 2 equals 0 or cannot equal 0. So x cannot equal negative 2. There's our vertical asymptote as well. So x is such that x cannot equal negative 2. But now we do need to make sure that we don't have any, like, where's our y and x intercepts? So y-intercept is the one where we set x to equal 0. So y equals 1 over 0 plus 2 minus 3. So y equals a half minus 3. Y equals negative 2.5. So our y-intercept is 0, negative 2.5. So that is going to be, hold on a second. Y-intercept, yes, that's correct. I was looking at the x-intercept. So that's where it's going to cross the y-axis. Okay, then we need our 0, our x-intercept, which means that we're going to set y to equal 0. So 0 equals 1 over x plus 2 minus 3. I just want to check how much room I've got here. Okay. So we're going to add 3 to both sides. 3 equals 1 over x plus 2. Now, what I'm going to do, I'm going to take this over here. I'm going to go ahead and multiply by x plus 2 both sides. So I get x plus 6 equals 1. And then, hold on, something's not right. 3x plus 6, of course, because I'm multiplying the 3 with both. Subtract 5, so we get 3x, or subtract 6, I'm sorry. So we get negative 5. Divide by 3, we get x equals negative 5 thirds. So this is negative 1 and 2/3, just to get kind of an idea where it is. So it would be right here. Okay, let's sketch it. So it's going to come down here and then go all the way here. The other part is going to be right here. Remember that these are our asymptotes. Okay, our 0 was the x-intercept, which is negative 5/3 to 0. Our range is going to exclude negative 3. So negative infinity to negative 3, or negative 3 to infinity. And our end behavior, when x gets closer to infinity, y gets closer to negative 3. See right here, x is going to infinity, it's getting closer to negative 3. Same thing for the negative infinity, y gets closer to negative 3 on this side as well, but never reaches it. Okay, next thing, horizontal and oblique or slant asymptotes. These are the harder ones. The vertical asymptotes are the easier ones. So these asymptotes apply primarily to the end behavior of the function and can sometimes be crossed. Remember that. Will not be more than 1, determined by the degree of the numerator compared to the degree of the denominator. Remember, degree is the largest exponent, so that's what we're looking at. There are 3 cases for the horizontal or slant asymptotes. So if the degree of numerator is less than the degree of the denominator, that means that our horizontal asymptote is our x-axis. So y equals 0. For example, if we have f of x equals 1 over x, our degree of numerator in this case is 0 because there's no variables, and our degree of denominator in that case is 1 because it's only x. So 0 is less than 1. If we do another example, g of x equals x squared over x cubed. Again, degree of numerator is 2. Let's do x cubed plus 1 here. And the degree of denominator is a 3. 2 is less than 3. So for both of these, our horizontal asymptote is y equals 0. Okay? Our next case is when the degree of the numerator and the degree of the denominator are equal. That is when the horizontal asymptote is the ratio of leading coefficients. Or we use the term leading terms in, I think it was the previous lesson that we did. So an example of this one would be f of x equals 3x plus 5 over 2x minus 7. You can see that the degree of the numerator is 1 and the degree of the denominator is 1 because we only have the x's. So what we would do is we would take the leading coefficients and write down the ratio. So horizontal asymptote would be y equals 3 over 2, and that's it for this one. Now, if we look at, for example, another, let's do g of x equals x cubed minus x squared plus 7 over 2x cubed plus 5. And again, These both are degree 3. So we would take the leading coefficients of the, um, or do the ratio of leading coefficients. Remember that this is a 1, even though it's not marked. So our horizontal asymptote for this would be y equals a half. Okay, then we have our third one, where the degree of the numerator is greater than the degree of the denominator. And that gives us a slant asymptotes. So all we are going to do is say that it is a slant asymptote. We're not going to be solving for, you know, the slant asymptote in this course. So if greater by 1 degree, notice if it's greater by 1 degree, then we have a slant asymptote. And again, not to find, only to recognize. Um, so for example, if we have f of x that equals 3x squared plus 5 over 2x minus 7, we see that our degree of numerator is 2 and our degree of denominator is 1. So 2 is greater than 1. And since it is only greater by 1, that means that there is a slant asymptote, and that's it. Okay. We actually already looked at the horizontal asymptotes and the slant asymptotes uh, on the first page. If you want to go back and kind of look at why, um, you can always, of course, do that. So, for example, in this first one, the degree of the numerator is less than the degree of the denominator because it's 0 and 1. So that is why our horizontal asymptote is y equals 0. Same thing here. The degree of the numerator is less than the degree of the denominator. So our horizontal asymptote is y equals 0. This one here, number 3, we have the degree of the numerator is 2 and the degree of the denominator again is 1. So 2 is greater than 1 by 1 degree. So that is when we know that our slant asymptote is going to be y equals x. But again, we don't need to know that it's this part right here. You just need to know that it has a slant asymptote, if that makes sense. If you're able to figure it out from a graph, then great, but you don't need to. Okay, number 4, our degree of the numerator is 1 and degree of the denominator is 2. So that means that our horizontal asymptote is y equals 0. Okay, let's move on here to practice a little bit more. So here we're supposed to find the horizontal or slant asymptote for each rational function. Um, so our degree of numerator and the degree of denominator. The degree of numerator is 1, degree of denominator is 1. So that means that they are equal. So we're going to do the second one where it says ratio of leading coefficients. So our leading coefficients here is y equals 2 over 1, which is 2. So it's y equals 2. Okay, next, again, our degree of numerator here is going to be 1. Our degree of denominator is going to be 2. So 1 is less than 2, and that is our first case where our horizontal asymptote is going to be y equals 0. Okay, next one, our degree of numerator is 3, and our degree of denominator is 3. So, oops, did I write x? I meant to write 3. These two equal, and that means that we're going to take the ratio of the leading coefficients. So y equals 6 over 6, which is 1. So our horizontal asymptote is y equals 1. All right. We're going to now look at how do we graph rational functions. Again, this is kind of sketching. So what we need to do first is define the domain. Then we factor and cancel if necessary. If a factor in the denominator cancels, it causes a hole, not a vertical asymptote. Then we're going to find the horizontal asymptote by comparing the degree of numerator to the degree of the denominator, just like we did in these last two examples. Then we're going to set the denominator to equal 0 to find any vertical asymptotes. Then we're going to find the y-intercept if x equals 0 is in the domain, and find any x-intercepts if y equals 0 is not a horizontal asymptote. Notice those if sentences. Then we're going to pick x values in the intervals between and outside the asymptotes to plug in. Okay, so those are the steps that we're going to do. Let me just do this again here. So I'm not running into the other space. Okay, we've got y equals 3x over x minus 1. X minus 1 cannot equal 0, so we know that x cannot equal 1. So that is our domain. X is such that x cannot equal 1. At the same time, or not at the same time, what I meant, what we're going to do, sorry, is we're going to look at this, sorry, I had our function here. Is it factored out already? That's the question that we're going to ask. And we see that yes, it is. So we will only have a vertical asymptote, no holes for this one since we're not factoring anything out. And our vertical asymptote is going to be that x equals 1. Now we need to figure out our horizontal asymptote. Well, for that, our degree of numerator is 1, degree of denominator is 1, so those are equal. So that means that we're going to take the ratio of the leading coefficients. So our horizontal asymptote is going to be y equals 3. Remember, there's a 1 in front of that. Next, we need to figure out the x and y intercepts and if we need any additional points. Our y-intercept is going to be x equals 0. So y equals 3 times 0 over 0 minus 1. Y equals 0 over negative 1, which is 0. So our y-intercept is going to be 0, 0. Then we're going to figure out our x-intercept, set y to equal 0. So 0 equals 3x over x minus 1. Well, we're going to have to multiply by x minus 1, which means that these cancel out, and then we get a 0 equals 3x. And now we divide by 3, which means that x is going to equal 0. So we get the point 0, 0 again. We could have looked at the y-intercept and realized that, okay, it is 0, 0, so it's going to be the same point. Okay, so here's our x and y-intercept in the origin. Then we're going to graph our asymptotes. X equals 1 is going to be right here, and y equals 3 is going to be right here. Okay, we need a couple of points here before we are able to graph this. Now, what we're going to look at is how does it behave right, like near the asymptotes. So what happens when x is, for example, 2? So we're going to plug in 2. 3 times 2 divided by 2 minus 1. Well, that's going to be 6 over 1, so that's 6. So our point is 2 and 6 right here. Okay, well, that's not going to give us that much of an idea. Let's plug in 3. 3 times 3 divided by 3 minus 1. So 9 over 2, which is 4.5. So when x is 3, this is going to be 4.5. Okay, that's giving us a little bit more of an idea of how it's going to go. Let's do the other side. So we already know that it crosses in 0, 0. What we want to know is where is x equals negative 1. So we're going to plug in 3 times negative 1 over negative 1 minus 1. So negative 3 over negative 2, so it's 3 over 2, which is 1.5. So negative 1 over here. Negative 2 is 3 times negative 2 over negative 2 minus 1. Negative 6 over negative 3, which is a 2. Negative 2 and 2 is over here. Okay, now we know that it's going to approach that y equals 3, but never touch. The same thing here for the x equals 1. So that part is going to look like that. Well, this is going to look very similar where it's going to again approach x equals 1 and y equals 3. Okay. And like I said, this one didn't have any holes because it doesn't we didn't factor anything out. All right. One more example here. Y equals x minus 2 over x. So denominator, x cannot equal 0. So we know that the y-axis is going to be one of our asymptotes. So our domain is going to be x is such that x cannot equal 0. And now we're not factoring anything out, so we don't have any holes. X equals 0 is going to be our vertical asymptote. Our horizontal asymptote now, again, oops, what did I do? Zoomed it somehow. Okay, here we go. That looks better. um, Hold on. So our degree of numerator is 1, degree of denominator is 1, so those are equal. So what do? We take the ratio of the leading coefficients, which in this case is going to be 1. So y equals 1. Here we go, right here. Okay, next we're going to calculate the x-intercept and the y-intercept. Um, Now, looking at our asymptotes, I mean, we can go ahead and try it, but as you can see, our y-axis is actually the vertical asymptote. So that means that we don't have any y-intercepts. The graphs are not going to cross the y-axis, but x-axis, yes. So let's go ahead and set y2 equals 0. So we get 0 equals x minus 2 over x. We're going to multiply by x both sides to cancel these out. So we get 0 equals x minus 2. So 2 equals x. Our point is 2, 0, where it crosses the x-axis right here. Um, okay, so we're going to need a couple of additional points here. Um, for us to be able to graph this. Let's do x equals 1. So 1 minus 2 over 1, that's negative 1 over 1, which is negative 1. So we have 1, negative 1 right here. We know that it's going to approach y equals 1, and we know it's going to approach x equals 0. So it's going to look like this. Now, next, let's look at the negative x values. So let's plug in x equals negative 1. Negative 1 minus 2 over negative 1, which is going to be a positive 3. Negative 1 and 3 is right here. Let's do negative 2 just to make sure. Negative 2 minus 2 over negative 2. So 4 divided by 2 is going to be 2. So that's going to be right here. And again, we know that it's going to approach x equals 0, and we know that this is going to approach y equals 1 and never touch. Okay, that's it for this lesson. Let me know if you've got any questions. Bye.